Michael?
Thank you, and thanks to everyone for inviting me here. I'll try to walk through some of the chemistry that gets involved in the air pollution problem, the particulate matter problem in the San Joaquin Valley, and hopefully we can draw out some of the issues that have already been identified. And I'll be referring back to the CRAPAC study as the other speakers did, because that's the information that we have right now. It was a great study that was done 10 years ago, and it's given us a wealth of information, and we're still digesting some of that. And until the CalNext results become available and we learn a lot from that, then we'll be ready to move on. But for right now, CRAPAC is where all of our information is. I think everyone recognizes that there's health effects associated with particles, and so I won't dwell on this too much. That we know that the increased particle concentrations are associated with an increased death rate, and so that then motivates EPA to set regulations, and we try to meet those regulations by understanding the sources and controlling them. And where do we have problems across the United States? This is data from EPA's Speciation Trends Monitoring Network for airborne particles with aerodynamic diameter smaller than 2.5 microns, so 2.5 microns and smaller. And this is the annual average picture, and we can see that there's hot spots in some locations, particularly in California. There's hot spots in Los Angeles region. There's hot spots in the San Joaquin Valley. If we would look at the 24-hour average monitoring standard, these trends would still be there, and perhaps even worse. California does have a unique problem across the nation. And if we wanted to take a drill down then into the San Joaquin Valley, where are the particles concentrated in the valley? And looking at the data from the CRAPAC episode, as other presenters have mentioned this morning, we can see that there is differences across the valley. The northern valley tends to be less polluted. The southern valley tends to be more polluted with respect to the mass of airborne particles. And we want to understand the sources and the chemistry that's producing that. The other question that comes up then is when are the particle concentrations the highest? And this is also something that's been dealt with by the other speakers this morning already. We can see this is a look at an annual average measurement campaign, different locations in the different panels, and you've got date along the lower axis, starting in December of 1999, going all the way to February 2001, so more than a year of data here. And you've got the PM 2.5 concentration then plotted on the vertical axis for each of those stations. And what quickly becomes apparent is that we've got the highest concentrations happening in the winter months. November through January is when we tend to develop those really high concentrations. It's not as if we don't have any particles during the summer, but we're not getting the things that are really violating the standard by large amounts in the summer. We're getting them in the winter months. And so what are the sources and what are the chemistry that are responsible for that? And David charged me with answering some questions, which I'll try to do justice to in the 45 minutes that I have. What are the sources of PM 2.5 in the region, and why do they concentrate in the winter? Primary versus secondary species. Primaries, we'll go through the definitions of these things a little bit later, but primary is basically directly emitted as a particle from a source. Secondary is it's emitted as a gas, and through the magic of atmospheric chemistry, then forms particles in the atmosphere. Where and when do the PM 2.5 concentrations vary in the valley, and then what types of control measures have been successful? And you know, the highlights, the home runs have already been hit upon by the previous speakers. You know, the wood smoke issue, the issues related to nitrate formation from NOx. And so we'll walk through that and try to flesh it out a little bit more, but you probably already have the really big success stories. You've already heard about them today. We'll just try to go over them a little bit more. You all know about the San Joaquin Valley. I threw this in here more or less to remind me of what to say on the next slide. Just take a look at the San Joaquin Valley and how big it is. There's 3 million people living in the valley. And it's the lower part of the central air basin here. Look at the South Coast Air Basin, which is on there below the San Joaquin Valley, the coastal area around Long Beach. I should have put slides on this. I missed the pointer as well, but I think everyone knows where Los Angeles is. There's 15 million people living there in a much smaller, more confined air basin. So it really is kind of unique and puzzling of why we have an air quality problem in the San Joaquin Valley that rivals Los Angeles. And it really is an issue to try to dig our teeth into. Now, we have very large industries in both those air basins. There are different types of industries. There are different types of agricultural practices happening here than there are in Los Angeles. But it's still quite interesting. Well, if you just take a look at the topography around us, and we have very high mountain ranges on all sides of the valley. We get high pressure systems that move in. This is my very crude attempt at, it's the only one I'm going to bother you with today, I promise. No more animations after this, but I know you're all in awe. So the high pressure systems moving into the region, stagnating over the valley, put the lid on the box, so to speak. Basically, if you have hot air trapped above cold air, you're not going to get mixing. That's going to cap the box. And so this is a typical temperature profile as you move up in the atmosphere during one of these high pressure stagnation events, and you've got hot air trapped above cold air, and you effectively cap the box. Now, that traps all those emissions where we breathe, and it allows all the chemistry to happen, and we end up forming these very high particulate matter concentrations. This next slide is just a little bit of a data shot for 3 years looking at how the height of that box sort of varies with the season of the year. And so along the lower axis, I've got the time of year, January through December. Along the vertical axis, I've got the average height of that mixing depth. And I shouldn't have shown 3 things on here. What I'd like you to concentrate on is the gray line, the continuous gray line. And that's the measurements of that height of that mixing depth, the height of the box, how deep is the box that we're mixing those emissions into. And it tends to be highest in the springtime. It tends to decrease during the summer, and it also tends to decrease during the winter months. And so right away during the winter months, you tend to have a lower height on the box. You're going to concentrate things more because it's a smaller box that you're mixing the emissions into. So that's part of the reason why we're getting higher concentrations during the winter. This is also not a great graphic, but I put it in here to remind me what to say about this. The sources change. We tend to have fairly cold temperatures in the valley during the winter, pushing freezing during the winter time, and home heating becomes a big issue then. And wood burning was one of the primary ways that folks would use to heat their houses in the winter, and now you've got a smaller box, and you've got new emission sources being emitted into that box during the winter time, and that is also contributing to why we get the most severe events during the winter. So some basic particle chemistry, and these terms have been thrown around. And there's a lot of acronym soup when you talk about this. There's always acronym soup when you talk to anybody about their fields. They start throwing short forms of words at you, and you quickly get lost. And so primary particulate matter is particles emitted directly to the atmosphere from a source. Secondary particulate matter is emitted as gases, and then atmospheric chemical transformations turn some of that material into particulate matter. There's a variety of different chemicals that contribute to both primary and secondary particulate matter. You heard Ajit say elemental carbon EC and organic carbon OC. Those are blanket terms for thousands of different compounds that exist in the condensed phase that contain carbon. And generally speaking, the elemental carbon is less volatile. It's more sooty, black. If you heat it up, it wouldn't go back to the particle phase. Organic carbon tends to be more volatile, or if you heat it, it will tend to evolve into the gas phase a little bit more easily. It contains more oxygen, hydrogen, and so on. On the gas side of things, the main players are the oxides of nitrogen, and most of that is emitted as nitric oxide, NO. And then we have emissions of ammonia, which is mostly coming from agriculture in this region, although there are other sources. And those combine through atmospheric chemistry then to give you particulate nitrate, which is the other big chunk of the airborne particles during the wintertime. You've got some sulfur emissions, SO2 emissions, but it's not as much of an issue here as it is in other places in the country. And there are also emissions of volatile organic compounds that then participate in the chemistry. These are the things that will produce a lot of oxidants in the atmosphere, generate a lot of ozone during the summertime. They can also generate particles. So that same chemistry can make particles. And there's a lot of subtle details about all of this. Some of that primary material can actually evaporate and go to the gas phase where it may react chemically, and then it can come back to the particle phase. I can talk for a whole hour or more on that. Certainly more of my colleagues can do a better job of that. But we won't go into that level of detail here. We're going to try to stick on the main topics, the thing that's dominating most of the particulate matter in the atmosphere, and focus on that. So I wanted to try to show some seasonal differences and also some location differences, and so I stole a picture out of the same article that Judy Chow wrote that other people have been referencing today. And these are spatial transects. So if we would draw a line through the valley and look at the variation of the concentration along that line, how would things look in the spring, summer, and fall, the periods when we don't tend to have as high concentrations, or in the winter when we do tend to have high concentrations. And the thing that I want to start